So why am I talking about Scala? A year ago, I would have never seen myself as a Scala developer. But a year ago, I also ran into a crossroad with my career. And this was a crossroad that was brought about because of BTI 360's leadership, basically challenging me to update my skills. So see, the last 10 years, I've been a web services developer. And I kind of came to the realization that my skill set was kind of a dime a dozen. I was seeing cheaper, younger developers come in that had the same skill set as myself. So I decided, well, what am I interested in? So I decided to pursue opportunities in big data. Well, I soon found out there was a problem. My current skill set, as good as it wasn't enough to allow me to actually even get into the door. I couldn't even get an interview, which this was like the first time in my career I've actually run into this problem. It was a little crazy and stressful for me, and so I was trying to figure out what can I do? You know, I can't get enough experience to get on a project. So the BTI 360 leadership suggested, why not look into Scala? Scala is a language that is used in a lot of big data spaces. So I decided to look into Scala, took a couple online courses through Coursera, and now I've ended up on a contract that is using Scala. And so really it was my entry into getting into big data. So there's two takeaways that we're going to have from this talk. One, why are we even talking about Scala? And two, okay, Scala, but why is it still relevant in a Java 8 world? Before we get into why Scala, let's look into the criteria that we want in terms of choosing a language. So what do we really need in a language? Well, first off, it has to be the right solution for the problem. If it doesn't work, then there's no use to look at it. So one language can't fit all, and one language can't be the best solution for every single problem. In addition to that, we need developer productivity. A language needs to be easy to use and allow a developer to write code as quickly as possible. In addition to that, we need to have great libraries. The greatest language in the world is useless without a strong ecosystem. We don't want to have to take the time to reinvent the wheel, nor do we want to have to work with buggy or incomplete libraries. So if a language needs to be the right solution for the problem, what are the problems that we're trying to solve? So the first problem is the need for massive parallelism. Things like big data and services like Twitter, which must handle 200 million users a day and 500 million tweets a day, require the need for massive parallelism. We also have a change in hardware. Up until 2008, clock speeds were increasing, and so in order to make a program faster, we would just throw bigger hardware at it. Well, that's not the case nowadays. Now, multi-cores, the number of cores are actually increasing, and so in order to make a program faster, we need to throw parallel hardware at it, not bigger hardware. Well, there's one problem. Parallel processing is hard. Anyone that's dealt with threads knows that parallel processing is not a trivial issue. Well, what is it that really makes parallel processing hard? Well, what makes it hard is shared mutable state. So let's look at exactly what we mean by mutable state. As soon as we add a setter, we have mutable state. But it's not just mutable state that's the problem, it's the fact that we share it. And what does this look like? So here we have a simple code snippet where we are initializing a value of x to 0. And we have two separate threads that are going to run. In these threads, in the first thread, we're going to grab the value of x, and we're going to add 1 to it, and then set a new value for x. In the second thread, we're going to get the current value of x, multiply it by 2, and then set the value of x again. Well, here's the problem. If I run this code, I can get 3 different values. I can get a 0, I get a 1, or a 2. This is the problem with shared mutable state. So then the question begs, what do we do about shared mutable state? What can we do? So a common approach is to use synchronization and locking. This approach works, but it can become problematic, because if we have too much synchronization and locking, then our performance starts to suffer. So what's another approach? So the best approach is to actually get rid of mutable state or minimize it. Well, what can we do to help us get rid of shared mutable state? Well, Scala can help. Scala was introduced in 2004, and Scala is actually an acronym for Scalable Language. The author of Scala, Martin Ordersky, was one of the designers of Java generics and is actually the author of the current Java compiler. So exactly how does Scala help us out? Well, first off, it's functional. It's a pure functional language, just like any other functional language, such as Haskell, Clojure, or Erlang. So what does a functional language gives us? Well, the one thing that functional languages do is that they eliminate the need for shared mutable state. Well, if what we need is a functional language, then why do we pick Scala? Why not pick Clojure or another functional language? Well, the reason is Scala is also object-oriented. So not only do we get a functional language, but we get a full object-oriented language as well. So we get the power of a functional paradigm without having to leave behind the power of an object-oriented language. So really, Scala is kind of like a functional language on training wheels. It allows developers to continue to code the way they're used to, and now they can introduce functional programming where it makes sense and where it's necessary. Another nice feature of Scala is that it runs in the JVM, and it is completely interoperable with Java. And so what this means is that Java code compiles down to class files, and we can actually write Scala code in Java and vice versa. And another great benefit of Scala being in the JVM is that we get to make use of Java's great ecosystem. We have 15 years of great libraries to use. So this means that as a developer, I don't have to leave behind my favorite library, whether it be Spring or Hibernate. So it's great that we have these great libraries, but a language is not useful unless it has a great community around it. We don't want another Betamax versus VHS going on. So who besides Ricky and myself is actually using Scala? There are a lot of large companies such as LinkedIn, Twitter, Sony, and Amazon that are using Scala. In addition to that, there are a lot of large projects such as Apache Spark, Apache Kafka, Apache Palo, and Akka. So up to this point, we learned that Scala is functional, it's object-oriented, and it runs in the JVM. But don't we get all that with Java 8? So why do we really need Scala? Well, Java 8 does introduce functional programming, but the problem is that Java 8 is not a functional language. It's really trying to play catch-up, and Java is not the only language that are trying to play catch-up to functional languages, so the functional programming is actually limited. Plus, Scala has a lot more to offer than just Java with functional programming. So Scala is all about developer productivity. In Fred Brooks' book, The Mythical Man Month, he argues that a developer would write the same number of lines of code per day regardless of the language that he uses. So he argues that if one language takes 10,000 lines of code and another language takes 20,000 lines of code, that developer can write a program with the first language twice as fast as with the second. Well, the nice thing about Scala is an expressive language. So this means that we can write code quickly as possible, and that it doesn't take a lot of code to do simple tasks. So let's look at some of the features in Scala that make a developer's life easy, and let's compare some of those with Java 8. So one thing about Java is it's verbose. This can be a good thing because it can make code readable, but it can also be a bad thing because it can require a lot of code to do a simple task. An example of a simple task in Java is the creation of a POJO. So let's look at what it would take to create a point class in Java. So we have a class. We're going to need state, so we're going to have to add some fields. Now that we have fields, we need to be able to initialize the values of those fields so we can add a constructor. Then we need getters and setters. And then, of course, we're going to need to implement the hash code and equals method. So this doesn't look too bad. This is a pattern that all of us have kind of seen more than we could probably count. And an IDE will even take care of a lot of this code for us. But the problem with IDEs is automated code is not always the greatest code in the world. For example, if you've ever seen the implementation of the equals and hash code method that Eclipse creates, it's pretty awful. So we could introduce something like Apache Commons and use equals and hash code builder to make life a little easier. But overall, we still have a lot of boilerplate code. So let's see what it takes to create this same class in Scala. One single line. So here with the case class, we get exactly what we got with the Java example. We get fields, we get a constructor, we get getters and setters, and we also get an equals and hash code method. So one thing that I will point out just for syntax is that in Scala, the variable name comes first and the data type comes second. But as you can see with this simple line and the expressiveness of Scala, we eliminate the need for boilerplate code. So there's been many times in Java where I wish I had multiple inheritance. So yes, it is true, Java 8 does provide multiple inheritance through default methods with their interfaces. But one difference is that Java 8 does not provide multiple inheritance of state. So Scala provides both with traits. So let's look at an example of a trait. So first off, we're going to start off with an abstract class called animal. This is very basic. It's going to provide some behavior through the method called speak that must be implemented by the extending class. Now we introduce a trait called four-legged animal. This looks very similar to a basic Java interface, where again, we're providing some behavior through some methods that must be implemented by the extending class. So here's the power of traits, though. Now we actually can define basic behavior and state as well. So in this case here, we have state through a value of tail length, and we also have a default implementation of start tail and stop tail. So now we can put this all together. So now here we have a class dog that extends both animal, wagging tail, and four-legged animal. So now dog is allowed to make use of multiple inheritance through traits because it's able to inherit behavior from multiple classes. So we talked about the number one enemy of parallel processing is mutable state. So how does Java and Scala handle immutability? So they handle immutability like night and day. So for Java, the approach is everything starts out mutable, and then we make it immutable if we need it. So let's look at what it takes to make the point class that we showed earlier mutable. So first off, the class needs to be made final. This because we don't want anyone to be able to override our class. In addition to that, our data or our fields need to be final as well, because we can't allow the fields to be changed. Our constructor must initialize all data that's required. So this means that we can't make use of default constructors or no argument constructors. And in addition to this, we're not allowed to provide setters, so we only have getters here. So Scala's approach is totally different. Scala's approach is, hey, let's make everything immutable and then use mutability when needed. So let's see how Scala handles immutability for the same class. This looks very familiar. Well, one thing that you'll notice that's different is, in this case here, we're not using the var. So a var in a case class means that I'm going to provide getters and setters, but the default implementation of a case class is an immutable class. So here we have the exact same thing that we have with the Java example, but again, with a single line of code. This, again, is the expressiveness of Scala. So not only do we need to have immutability for classes that we create, but we need to have immutability of underlying data structures in the language that we want to use. So how does Java handle immutable data structures? The same way it handles classes. It starts off with mutability, and then it uses a utility class to create an immutable view. So here are a couple of examples. We can use the arrays class to convert an array to an immutable list. Or we can start out with a mutable data structure such as a set and use these unmodifiable methods on a collection to then produce an unmodifiable set or map. So Scala's approach to go into mutability first and then mutability later, out of the box, all data structures are immutable. So here we have a list, a set, and a map. Now we can still add to these lists and set and map, but in order to do so, we actually create another list or set or map, and we don't actually modify the original. So here we can see that Scala does make immutability much easier. So most of you guys have taken the EDX Apache Spark course and know the power of being able to transform collections. So lambdas and high order functions give us that capability. And this is one of the capabilities that's been introduced into Java 8 as well. So let's look at how Java 8 handles it. So in this particular example here, we are taking a people list and we are going to filter and only provide persons whose first name is John. But the one thing that's different with with Java is that we actually have to take our collections and convert it to a stream class, because the stream is actually what has these high order functions such as filter, map, and reduce. So once we perform our transformation, what we actually get back as a result, again, is a stream class. We must convert the stream back to a collection. So Scala's approach is much different. Scala provides high order functions as part of the collection class itself. So here we have the exact same example where we're taking a people's list and we're filtering and only providing persons with a first name of John. But see, there's no need to convert our collection either when we're making the transformation or the result of the transformation. Here's another example of a high-order function in Scala. So the map function allows us to apply an operation on each element inside of our list. In this particular case, we are going to take our people's list and map it and create a list that contains only the first names for all the people on the list. We can use functions like reduce. Reduce allows us to take a list and perform an operation on it. In this particular case here, we're going to add all the elements in the list and get back a result of 6. For each is another example of high-order function. This actually allows us to apply a method to each element in the list. In this particular case here, we're going to use print line and print every value in the list. So I'm sure you've seen this case numerous times. We have a constructor that takes a lot of arguments, and most of these arguments are not even required. So in addition to that, a lot of times we want to make this immutable. So how do we do that? So a common approach is to use the builder pattern. So let's take a look at the builder pattern for this person class. In order to do the builder pattern, first off, we need to make the constructor private because we don't want to be able to allow creation of that class outside of the builder pattern. So we're going to introduce a static class called person builder. And as you notice, we need to have an additional setter for each field that we want to be able to set. And at the end, we can call build and return an instance of our person class using our private constructor. This is a lot of boilerplate code just to make an immutable class. Let's look at Scala's approach. So again, we come back to our case class. Here we have a person with the same fields that we had in the previous example: salutation, first name, middle name, last name, and suffix. And as you can see here, we're allowed to set defaults for all of these parameters. So we can call this constructor. So we can construct a person who is Mr. John M. Doe Sr., just like we could with a normal constructor. But here's the power. With this case class, we can actually get 32 different constructors by the use of name parameters. We can actually reference the name of the parameter when constructing a person. So in this particular case, let's say a valid person only requires a salutation of first name and last name. We can construct that person. Or we can construct a person which is a first name, middle name, and last name. Or let's say we only need a first name. Or just a last name. Or just one other example to show you the power of name parameters. Now, one thing to also point out is the order of the parameters don't really matter. So in one case here, we actually started out with salutation as our first parameter, which is our first parameter in our constructor. But in the second case, we start off with first name. Here again, we see the expressiveness of Scala. It actually mitigates the need for patterns like the builder pattern. So pattern matching. So there's many times in code where we need to validate input into a method or validate the way that an object is being constructed, make sure that it's been constructed properly. And in addition to that, a lot of times we want to be able to provide business logic for a specific flavor of an object. Well, pattern matching allows us to do that. Pattern matching is kind of like a switch statement on steroids. And this is one feature that Java does not provide. So let's see how we can use pattern matching. So let's say we want to parse some command line arguments for some command line interface. So if we start off with a method parse args that takes in a single string that's an argument. If we want to be able to match, then we can add this match expression. So now we're going to match on the arg parameter. So a simple example of a command line interface, what do we always do? We want to see what the help is, right? So let's match on help. So we're going to match on the case where the argument is either -h or --help. And in this case, if it matches, we're going to display our help. Well, we also need to handle the case where, what if they input an invalid argument? Now we have a default case. In this case here, if we get a bad argument, then we're gonna print out a message to the user and let them know that the argument was bad. So this is kind of useful, but not really, because most arguments have some type of value that goes along with them. So let's change our method. Now our parse argument takes not only the argument, but the value that goes along with it. So again, we're going to provide a match expression, but this time we're actually going to match on both arg and val at the same time. So if we look at what we had before, our case with help stays relatively the same. Now we just say we don't care about the value, so we're going to include null. But let's say now we want to provide a case. We have a case of -L where we're setting some language. Well, we need to know what the value of the language is so that we can set it. So in this case here, we're going to mash on -L, and we don't really care what the language is. So whatever it is, now we're going to call our set language to passing in that. Well, what if we needed to actually validate the value of our argument? So in this particular first case here, we're going to pattern match on a -O or a -optim. In this case here, we want to provide some optimization level and provide a value whose range is valid between 1 and 5. And so here we can actually match the actual value to make sure that it's within this range. And if so, we can actually set the optimization level. Otherwise, let's match on O and optim again and provide a bad optimization level because the value is outside of our range. So as you can see here, patterns make it really easy for us to provide specific business logic based off of arguments for our method by matching on them. And in addition to this, we're also doing validation at the same time. There's no need to separate that. But let's look at some other different patterns within Scala. So we can do constant patterns. In the first case here, we can match on an integer whose value is 0. In the second case, we can match on a Boolean whose value is true, or a string whose value is hello, or maybe we even have a null case. We can also match on a sequence, or a sequence pattern. In this first particular example, we have a list that's a size 3 whose first element is 0. Or maybe we want to match on a list whose first element is 1, and we don't care how many elements it has after that. Or maybe we want to match on a particular implementation of a structure. In this case here, we can match on vector, or we can match on list. But the real power of patterns is the constructor pattern. So in this particular case here, we can actually match on a particular flavor of a class. In this case here, we're going to match on a person whose last name is Alexander. And we don't really care what the first name is, as long as the last name is Alexander. Or we can, in this case, we can match on a dog whose name is Suka. So this is a quote from Tony Hoare. And this is what he is referencing to is the financial impact of creating the null reference. And the reason why there's such a problem with null reference is that a method can actually return multiple values. It can return one value if it's successful, or sometimes it can return null if it's not. But there's really no way for us to know that other than either looking at the code itself or hoping that there's some documentation that specifies otherwise. But what if down the line even the code changes? Maybe it didn't return null before and now it does. So what we really need is we need the method signature to tell us that a method can actually return multiple values. So wouldn't it be great if we had that? Well, Scala does. Scala has the option. And the option is actually an abstract class that can be two different types. It can be a sum or a none. And in the case we return sum when our method is successful, or we return null when it's not. So let's look at an example how this is being used. So here we have a method that's going to convert a string to an int. And as you can see here in our method signature, we return an option that's going to basically wrap an integer. So we have two particular outcomes from this method. If we pass in a string that is not an integer, well then we're going to get a number format exception. And if we do, we're going to return back a value of none. Otherwise, if we're successful, then we're going to return back sum that wraps our converted string to an integer. So how is this actually being used? So here's an example. So if we call toInt and we pass in some string, we can use pattern matching, the feature that we saw earlier, to actually match on the two different cases. So in one case of the value of sum, where we're successful, we're going to print out the value of the integer. Otherwise, if none, we're going to let the user know, hey, that didn't work. You need to give me a different number. But collections also work really nicely with options. So if we have a list here that contains multiple strings, some of them that we can convert, some of them that we can't, we can use high order functions that we talked about earlier, like map. So if we were to use the map using our toInt method, what we actually get back is a list of options. And we'll get a value of sum for the 1, 2, and 3 that we could actually convert, and we'll get back none for foo and bar. But Scala even takes this a little step further. So options, the value of sum actually gets treated as as a collection of size 1, and a none gets treated as a collection of size 0. So we can use a method like flatMap, which will actually treat this as a list of lists. And so if we call flatMap and use our toInt method, we actually get back a list containing the values 1, 2, and 3. So as you can see here, options are nice because it allows us to know that our method is going to return back multiple values, and now we don't have problems that we have with null pointers. So as we saw, because of software and hardware trends, there's a need for massive parallelism, right? And we need to have a solution for that. And functional languages are a good solution because the enemy of parallel processing is shared mutable state. And functional programming stresses immutability and gets rid of shared mutable state. But we could have gone with any functional programming language, right? But we decided to go with Scala. And the reason being is because it's object-oriented. So not only does a language need to be the solution of the problem, but it needs to allow a developer to write code quickly. So by being object-oriented, we can continue to operate like we normally would and only introduce functional programming where necessary. In addition to that, Scala is very expressive. So we saw Scala removes the need for boilerplate code and makes life much easier for a developer. In addition to that, we saw that Scala works in the JVM, which is great because now we can make use of this great ecosystem that Java already provides and a strong suite of libraries. And we answered the question, is Scala still relevant in a Java 8 world? And the answer is yes. So even though Java has made great strides towards providing functional programming language, it is still not a full functional language, and it doesn't have all the things that we need in order to do functional programming. In addition to that, though, we also learned that Scala is much more than just Java 8 with functional programming because it gives us the developer productivity and allows us to write code quickly as possible.
Thanks, guys.